All right, everybody, this is lecture 7-8. You all voted for it to be a video lecture. And so we're talking about double and half angle identities today. These are the last set of properties that are going on your trig identities handout. And you have space on page 13 to write these as well. So I would say for this video right now, the expansions for the cosine of 2a, the sine of 2a, and the tangent of 2a, pause this video, write these down on your trig handout or on page 13 of your notes, and then play the video again to get the half argument properties, and then we'll use them in the examples below. So these are the expansions for the sine, cosine, and tangent of 2 times an angle. If you are interested in the proofs on how we get these identities, that will be included in the lecture slides that I post on the class website. So I'm not going to talk through them just for sake of time, but these are the properties that we call the double angle properties. Pause the video, write them down. All right, half argument properties look like this. So the cosine of half an angle, the sine of half an angle, the tangent of half an angle. Again, pause this video, write these down, and then come back when you guys are ready to go. I'm going to move on. I will say one thing. The cosine, sine, and tangent expansions for half an angle that have the square roots in them become the most difficult properties to apply. I think of all of the ones on your trig sheet, these are the trickiest ones, which means because there are 2 other expansions for the tangent of half an angle, we will pretty much never ever use that one because that one is way more complicated than the other 2 expansions for tan of half an angle. We don't have a choice when we're expanding sine or cosine of half an angle. We do have to use the square root. And I'll show you guys in the examples how I expect to see your answers. But the trickiest part is going to come from trying to evaluate whether the sine or cosine of half an angle is positive or negative. You're never going to leave your answer with that plus or minus side. And this is the part of 7-8 that is just a little tricky. All right, so let's do these example problems. On the bottom of page 13, we've got this information. We want to draw the diagram, write out the formula, show the substitution. These are all things you're going to do for your homework, and then we'll evaluate. So I've got the trig properties over here on the right-hand side, and we're going to reference these as we go. Here we go. In example A, we're told that the cosecant of theta is -5, and we're told that the tangent of theta is greater than 0. The last thing on your handout that we're told also is that theta is between 0 and 2 pi. Well, that's not as helpful as the rest of the information here. So we kind of have to interpret this, and the first thing we're going to do is we're going to draw the diagram to represent this. So we're told that the cosecant is negative and the tangent is positive. So we have to think back to the quadrants. Goes this way. Salty sea. Okay, where, in what quadrants are what trig functions positive and negative? So, first quadrant, all trig functions are positive. Second quadrant, sine and its reciprocal cosecant are positive. Third quadrant, tangent, cotangent. Fourth quadrant, cosine and secant. So, what quadrant has cosecant negative, which also means sine is negative, and tangent positive? That would be down here in the third quadrant. Tangent's positive, everything else is negative. So we have an angle sitting in the third quadrant. So I'm going to construct the third quadrant only. Don't care about anything else. I'm going to draw my angle in the third quadrant, drop the perpendicular to the x-axis always, and we're going to complete the diagram. Now, we're told that the cosecant here is -5. I can turn this into a fraction by writing it over 1. And now we know that the hypotenuse of this angle, of this triangle that we've created here, must be 5. Cosecant is the reciprocal of sine, which means that the y component is -1. Remember that the hypotenuse is never negative. It comes from the Pythagorean theorem. It comes from taking the square root of 2 squares, the sum of 2 squares. It's never negative. And then we just use Pythagorean theorem in order to find that missing side length, right, that x component. So it becomes the square root of 24, which is 2 root 6, but it's in the third quadrant, which means the x component here is negative. All right, so we've got our diagram for theta. Now we're going to use the expansions of the sine of 2 theta, the cosine of 2 theta, and the half angle expansions in order to solve the rest of these problems. So Sine of 2 theta, it's got one expansion here. And that expands to 2 sine theta, cosine theta. And then we're just going to substitute. So 2 stays. The sine of theta, if we look at our diagram, that's negative 1/5. The cosine of our diagram is negative 2 root 6 over 5. All right, final answer here. It is looking like positive 4 root 6 over 25. Can't simplify any more than that. All right, how about the cosine of 2 theta? Well, we've got a few expansions for the cosine of 2 times an angle. Doesn't matter which one you use. Stick with the one that you think might be the easiest. So in this case, I'm going to use the one with only sine because in our diagram, sine doesn't have a radical. I don't know. There's no other reason I'm choosing that. So I can expand the cosine of 2 theta as 1 minus 2 sine squared of theta. So that's going to give me 1 minus 2 times sine is negative 1/5. Don't forget that we're actually squaring that number. So we get 1 minus 2 times 1 over 25, which is just 1 minus 2 over 25. Final answer when I simplify, 23 over 25. Okay, down to 3 and 4. We're taking the sine of theta over 2 and the cosine of theta over 2. We're looking at the half angle expansions here. So, before I do anything, let's talk about theta and theta over 2. We have 2 expansions for sine of half an angle and cosine of half an angle. And both of those expansions require us to take the square root, which means that we have to figure out whether sine or cosine of half our angle is positive or negative. All right, so let's think about this. We know theta is in the third quadrant. Okay, theta is in the third quadrant because that was the quadrant where cosecant was negative and tangent was positive. That came from the beginning of this problem when we were trying to draw the diagram. So here's how I'm going to represent that. Theta falls between pi and 3 pi over 2. That tells us theta is in the third quadrant, right? Because 180 is pi radians, 3 pi over 2, that's our 270 degrees. This is where it gets tricky here. Now, we want to know what the sine of half theta is. And we want to know what the cosine of half theta is. So if I take our theta, our inequality here, our compound inequality, and I divide everything by 2, then theta over 2 is going to lie between pi over 2 and 3 pi over 4. Okay, I need you guys to even pause this video if you need and just kind of grapple with that. Theta was in the third quadrant, so theta is between pi and 3 pi over 2. We got that because cosecant was negative and tangent was positive at the beginning of this problem. The third quadrant is where that makes that true. And then to get theta over 2, I just divide everything about that inequality by 2. We get that half of our angle, theta over 2, has to be between pi over 2 and 3 pi over 4 then. Remember, I'm doing this because we're evaluating the sine of theta over 2 and cosine of theta over 2. And the expansions for half angle properties for sine and cosine require us to figure out what the sine is, plus or minus. Don't know yet. All right, once we've got theta over 2, I'm going to draw this angle, okay, or this range here. Pi over 2, that's the positive y-axis, 90 degrees. 3 pi over 4 is sitting out here, okay? That's 3 pi over 4. That's pi over 2. Our angle, theta over 2, has to be between those two values. So our angle, theta over 2 now, exists in that shaded region. So in that shaded region, is sine positive or negative? Think about it before you actually hear me give you the answer. But in that shaded region, is sine going to be positive or negative? If you guessed positive, you are correct. So our sine expansion is going to be positive something. Okay, positive square root of all of that. Same angle, okay, theta over 2. Is the cosine positive or negative? In that orange shaded region where theta over 2 exists, is cosine positive or negative? In this case, it's negative, which means that our fourth expansion here is going to be negative square root of something. Okay, so our third answer will be positive. Our fourth answer for this example will be negative. Comes from finding the region where theta over 2 exists. It's the trickiest part of this lecture. If you guys can get that, I think everything else is relatively easy today. All right, for sake of work, I've got to erase this. If you've got questions, drop in office hours. But let's apply those expansions now. I know theta over 2 is in the second quadrant where sine is positive. So I'm going to expand this now using the expansion 1 minus cosine theta over 2. And then I'm just going to fill in what we know. All right, I'm going to pull a 1/2 out of everything. I can do that. And then I'm going to get one minus the cosine of theta from our diagram was negative 2 root 6 over 5. And now we simplify. Now, I don't require you guys to simplify this too much. They just get a little bit complicated. So all I need you to do is get rid of that minus negative by making it positive, and that's it. You guys are welcome to stop there, box your final answer like that. Okay? Totally good with me. All right, last example on page 13, we're going over and calculating the cosine of half this angle. So remember that the expansion for cosine of half an angle is 1 plus cosine theta over 2, the square root of all of that. Now we know our final answer is negative because our angle, theta over 2, sits in the second quadrant where cosine is negative. So I'm going to do the same thing here. It's negative square root 1 plus cosine theta over 2, and I'm just going to fill in what I know. Okay, I can pull a 1/2 out of everything, and then I get 1 plus the cosine of theta was negative 2 root 6 over 5. And like I said, not a lot to simplify, just make the signs look nice here. So this is just going to be minus 2 root 6 over 5 like that. Don't even need to worry about finding a common denominator. They just get really complicated if you start doing stuff like that. All right. So moving on to page 14 of the note packet, example B, we're kind of going backwards now. So we want to use the unit circle angles to evaluate. We don't want to do this with a calculator. So we're going to take a look at the angles we've got and see if we can use the half angle formulas in order to write these in terms of angles on the unit circle. So in this example, the cosine of 15 degrees, well, 15 degrees is also 30 degrees divided by 2, all right? And I know actually it's probably easier to express this as like the cosine of 45 degrees minus 30 as A minus B. I like those better than using the half angle formulas, but today we're focusing on practicing the half angle formulas. So I'm going to use 30 over 2 here instead. Okay, so what do I know about the expansion here? Well, I know that when I expand, right, we get plus or minus 1 minus the cosine, plus the cosine of theta over 2. That's the expansion for the cosine of half an angle. Now our angle here is 30 degrees, right? It's the numerator or whatever number over 2 that is. So here we're going to have plus or minus the square root of 1 plus the cosine of 30 over 2. And we can evaluate the cosine of 30. The cosine of 30, just go to 30 degrees on your unit circle. That is the square root of 3 over 2. And then we simplify. And like I said, we're just going to keep it real simple. Use the same set of steps that we used in the last examples. The one thing is this. We've got to figure out plus or minus. We cannot leave that plus or minus. So go back to that original angle. The cosine of 15 degrees. 15 degrees is in the first quadrant. All right, cosine is positive in the first quadrant. So our final answer must be positive square root of all that. Okay? Pretty easy once you get past figuring out what the signs of these angles look like. All right, how about the sine of negative 15 degrees? Well, the sine of negative 15 degrees, let's think about where negative 15 degrees is. Okay, down here in the fourth quadrant, which means our final answer is going to be negative. Sine is negative down there in the fourth quadrant. Okay, I can express this as the sine of half the angle, negative 30 degrees. And then we can use the expansion here. We know it's negative because it's in the fourth quadrant. Negative 1 minus the cosine of negative 30 degrees over 2. And we're just going to simplify. Negative square root 1/2 times 1 minus root 3 over 2. Final answer there. Box it, we move on. Okay, last one on this set of examples. Example D, we're taking the tangent of negative 7 pi over 12. Well, I argue that this can also be expressed as the tangent of 1/2 the angle, negative 7 pi over 6. And that is an angle that sits on our unit circle. All right, where is negative 7 pi over 12 though? If we think about where negative 7 pi over 12 is, remember pi over 12 is 15 degrees. So we're just going to be over here in that third quadrant somewhere, right? Moving negatively means we're moving clockwise through the unit circle. And tangent in the third quadrant is positive. But we also know we don't have to use the square root expansion for the tangent of half an angle. We've got two other expansions there that don't have that plus or minus signs. We don't even have to worry about it if we use one of those other expansions. So I'm going to use the expansion 1 minus the cosine of theta over the sine of theta, where theta is negative 7 pi over 6. All right, so the cosine here of negative 7 pi over 6, I'm going to show this step so you guys can see it, right? That's what we're evaluating. 1 minus the cosine of negative 7 pi over 6 over the sine of negative 7 pi over 6. All right, the cosine of negative 7 pi over 6, if we go to the unit circle and we look at that, that's negative root 3 over 2. And then the sine of negative 7 pi over 6 is 1/2. All right, simplify these things a little bit. This is 1 plus root 3 over 2 over 1/2. And then if I just multiply by 2 over 2, I can get rid of those fractions. We get 2 plus root 3 over 1, which is just 2 plus root 3. Final answer there. Box it, we move on. We don't even have to worry about the plus or minus because I didn't use the expansion for tangent of half an angle. That requires us to evaluate. Last set of examples on the bottom of page 14, we're going to be using the double angle expansions now. So we just practiced a lot with the half angle expansions. We're going to talk about the double angle expansions next. So in example E, we've got the cosine of 2 times the inverse cosecant of 13 over 5. So remember, inverse trig functions give us angles. I have some angle A. So this all boils down to the cosine of 2 times this angle A. We just need to figure out what this angle A is going to look like. And we're going to do that by drawing a diagram. Okay, so a diagram for angle A. We've got inverse cosecant here. Remember that inverse cosecant is going to carry the same range as its reciprocal inverse sine. We're looking at an angle in the first or the fourth quadrant. Because this is positive 13 over 5, we know our angle must be in the first quadrant. So I'm going to construct an angle here in the first quadrant. This is going to be my angle A. And in order for the cosecant of this angle to be 13 over 5, that means that the hypotenuse needs to be 13. The y component must be 5. And using Pythagorean triples, we know that the x value here is 12. All right, we've got 3 expansions for the cosine of 2 times some angle. Pick one of them. It really doesn't matter which one you want. I'm going to use the cosine squared of A minus the sine squared of A. Works for me. And I'm just going to use the diagram here in order to figure out what the cosine of A is and the sine of A. Remember, we're squaring those values. That's the only tricky part here. The cosine of A is 12 over 13. That is being squared. And then we're subtracting the sine of A, 5 over 13 squared from that. All right, this is 144 over 169 minus 25 over 169. Just simplify before we go any further. 119 over 169 is the final answer here. So same thing on your homework, you guys. Draw the diagram when we're referencing an angle. Letter F, we're taking the sine squared. So that's really tricky. Don't forget that. We're going to find some value, and then we're going to square it. We're going to find the sine of all of this, and then we'll square that answer. That actually becomes really nice because we're taking 1/2 our angle, so we don't have to worry about the sign, the plus or minus there. Okay, so what does this become? Well, I have this inverse cosine here, which is going to represent some angle. I'll call it A. This problem then boils down to the following. This is the sine of 1/2 some angle A, that whole quantity being squared. And I think if you can rewrite it like that, it becomes a little bit easier to see. So before I go any further with the diagrams, I'm just going to write out the expansion for sine of half an angle. Remember that the expansion for the sine of half an angle is 1 minus the cosine of that angle over 2, the square root of all of that. But remember that we're squaring here, because the problem tells us to. It's the sine squared of all of that. So that square and square root end up canceling each other out. And so what this becomes is 1 minus the cosine of A over 2. Okay, let's draw the diagram to represent this angle A. We have an angle whose value is coming from inverse cosine, the range of inverse cosine. So between 0 and pi, first and second quadrant is where we're looking. The cosine is positive 3/5, which means in the first or the second quadrant, cosine is only positive in the first quadrant. Construct your angle in the first quadrant, drop the perpendicular, and what makes this angle have a cosine value of 3/5? Well, the x component must be 3, the hypotenuse must be 5. Using Pythagorean triples, we know that last side length is 4, which actually we don't need because we don't need the sine value when we expand. Okay, use this diagram. The cosine of A is 3/5. So we just have 1 minus 3/5 all over 2. Again, if I multiply by, I don't know, looks like 5 over 5, we can clear the fraction. We get 5 minus 3 over 10. That looks like 2 over 10, which is 1/5. Box that, final answer there. Okay, my suggestion to you guys would be to pause this video and try example G before I walk through it. See if you guys can do it before we go any further. All right, so pause the video now, come back in a minute. Okay, so this last problem is the secant of 2 times some angle I will call A. That angle is coming from the inverse tangent. Still an angle. We'll draw a diagram in a minute. But a couple of things that make this problem a little bit more difficult. We don't have the expansion for the secant of 2 times an angle, right? That's what this boils down to, is the secant of 2 times some angle A. But there's no expansion in the double angle identities that expands secant. So the first thing we're going to do is we're going to turn this into cosine. We're going to use the reciprocal property. This becomes 1 over the cosine of 2 times our angle. 3 expansions for the cosine of 2 times an angle. Doesn't matter which one you use. In this example, I'll just use 1 minus 2 sine squared. Okay, you could have used any of them. Now I just need to figure out what information this angle has. So we're going to draw the diagram for this angle. Inverse tangent has a range between negative pi over 2 and pi over 2. So first or fourth quadrant. In this case, tangent is positive 3 over 4, which means that our angle A is going to be in the first quadrant. That's where tangent's positive. What makes this angle have a tangent of 3/4? The y component must be 3, the x component must be 4. Using Pythagorean properties or Pythagorean triples, we know the hypotenuse is 5. Okay, now I just need to figure out where this substitutes. So we have 1 over 1 minus 2 times the sine of A, which is 3/5. But don't forget that we're squaring that. It's the sine squared of that value. All right, 1 over 1 minus 2 times 9 over 25. Okay, so keep that in mind. That's 18 over 25. And then we're just going to find a common denominator. I'm just going to multiply everything by 25 over 25. I get 25 over 25 minus 18. So that simplifies to 25 over 7. Box that. We're done. You're going to do your homework exactly the same way. Drop by office hours, you guys, if you have any questions, or shoot me an email.